All right, so today we have Luis Scoccola from Northeastern, who's going to be telling us about density-sensitive and robust Vietoris-Rips filtrations.
Okay, so thank you for the introduction, Facundo, and thank you very much for inviting me to speak at this seminar. The idea is to tell you about density-sensitive versions of Vietoris-Rips. And the basic example is we want to be able to handle data sets like this one that we can see have some sort of interesting topological structure, but Vietoris-Rips is not going to capture that because the topological structure has to do with density and not just with the metric. And the outline for the talk is to see some desirable properties of density-sensitive filtrations, then see some of the filtrations that at least I am aware of, and I'll tell you some of the properties that have been proven relatively recently. And then I'll end up with some open questions about how we may want to improve the current filtrations or the current results that we have for the filtrations. So let's start. So what's the goal? The very general goal is going to be to do a homological inference for metric probability spaces. And the reason why we may want to do that here is the following. Here are some applications. So one application that I'm very interested in is in doing density-based clustering, which is basically just identifying high-density connected components of some metric probability space from a sample. And then similarly, you may want to identify other topological structure like high-density loops or voids. And this, for example, comes up when you're doing time series analysis with a delay embedding. You expect to have some tori if the time series is relatively periodic, but you won't see the tori if there's too much noise in your time series. So you somehow have to get rid of some of the noise to actually see the topological structure. And then more generally, you may want to do exploratory topological data analysis, which just means I have some data set and I have some reason to believe that it has topological structure, but I don't know very much about the data. So I cannot just come up with a way of filtering it, like filtering out noise a priori, and I have to somehow look at it and see where the topological structure is, and only then try to filter it in some specific and more like context-dependent way. Okay, and I forgot to say, if you have any questions, please ask the question when you have it, because in theory, this should be shouldn't be a very long talk. So it's better to just ask the questions, I think. Okay, so what's the approach that we're gonna take? We're going to do the persistent thing. We're gonna try to find a construction that takes a metric probability space. So we're gonna interpret the input as having a metric and as having some sort of density structure. And we wanted to output a simplicial filtration that may have multiple parameters. So it could be a multi-parameter simplicial filtration, and we're gonna define that in a second. But basically, the only way to handle both metric and density is to have multiple parameters, at least as far as the current approaches go. And we want this construction to, at the very least, be density sensitive. So we have a construction like this. It's called Vietoris-Rips, and it just takes the metric structure into account. And we don't want that. We want to take the metric structure and the density structure. So we want it to be density sensitive. We would also like it to be stable, and we're going to make that precise in a second. And we also would like it to be parameterless. If we're going to allow to have for the filtration to be an n-parameter filtration, multiple parameters, then f itself, it would be nice if we didn't have to choose a parameter a priori. And then in an ideal world, we would get a robust filtration that is robust to outliers. And again, we're going to make that precise. And since we can always hope and dream, it would also be great if its homology was efficiently computable, and if it was easy to interpret in some sense that we will also make precise. So this is what we want, and the talk is going to be about these 4 filtrations: function rips, degree rips, kernel rips, and subdivision rips, and the properties that I basically just mentioned. and we're going to see which filtrations satisfy which properties, and then see what's left to do, basically. So let's start. So what is a simplicial filtration? An n-parameter simplicial filtration is a function that takes a vector of real numbers and returns a simplicial complex. And basically, all the complexes that it's returning are going to be subcomplexes of some fixed simplicial complex K. So these are going to be the values of F. And we want it to be, for F at R, to be a subcomplex of F at S whenever R is less than S in the pointwise order in the real numbers to the power of n. So this is a usual definition. And just to make sure that we're all on the same page, the Vietoris-Rips filtration of a metric space is a one-parameter simplicial filtration. Just has one parameter, if you want the distance scale. And what is it filtering? It's filtering the full simplex on X. So it's filtering the simplicial complex whose zero simplices or vertices are the points of the dataset X, and it has all possible simplices, and Vietoris-Rips is filtering that. In the end, you get all possible simplices, but in the beginning, you have only a few. Okay. Then we can go to metric probability spaces, the other piece of important definition. So what's a metric probability space? It's just a metric space together with a Borel probability measure. That means just it's a probability measure that is compatible with a metric. The main example, if you want to think about metric probability spaces, really all that's going to matter for us in this talk are metric probability spaces that come from finite metric spaces by endowing them with a normalized counting measure. So the measure of a subset of our point cloud or finite metric space is just the cardinality divided the cardinality of the full data set. And we want our filtration to take this notion of density into account somehow. So again, we want this kind of filtration. So and we want it to be stable. So we better give distances for these two collections of objects. And we're going to start with this one. And the idea is to have distances that take the probability or the density into account. We know of a distance here. We could take the Gromov-Hausdorff distance. But of course, that distance only takes the metric structure of the input into consideration. It doesn't consider any density information. So that's not going to be great. We're going to have to modify the Gromov-Hausdorff distance to take some density structure into account. But first of all, let's recall what the Gromov-Hausdorff distance is. So first of all, even before, what's the Hausdorff distance? The Hausdorff distance is defined for any two subsets of a common metric space, and it's just the infimum over all epsilons, such that, well, this should be X and Y. I guess. Sorry. So the Hausdorff distance between X and Y is the infimum over all epsilons, such that the Y is included in the epsilon thickening of X, and X is included in the epsilon thickening of Y. And this is just a usual metric thickening inside a fixed metric space. Then we can extend this distance to abstract metric spaces. Now they are not subspaces of a common metric space, they're just abstract metric spaces, and we can compare them by considering all possible Zs in which we can embed both X and Y, and then compare them inside of Z using the Hausdorff distance. And we can just take an infimum over all possible ways of doing this. And these have to be isometric embedments. Okay, so that's all fine and good. But again, this is not a great distance in terms of density structure, because it's forgetting about any measure or any density structure that X and Y may have. So in order to have a distance for metric probability spaces, what we're going to do is replace the Hausdorff distance by the Prokhorov distance. And the Prokhorov distance is similar in the sense that it allows you to take the distance between two measures on a fixed and common metric space. So you have two measures on Z, and you can take the distance between them, and it's something like the Hausdorff distance. You just want one of the, for every closed set of your metric space, You want the measure according to one to be bounded above by the measure according to the other one of a thickened closed set. And then you allow some epsilon that you may be missing to have this upper bound. And then you do the same thing on the other side. So the exact definition of this distance is not super important. The important thing is that it's telling us how similar two measures on the same metric space are. And it's using the metric structure into account because it has this epsilon here that has to do with the metric set. And then to extend it to abstract metric probability spaces, we're going to do the same thing as we did with the Gromov-Hausdorff distance. So if you're given two abstract metric probability spaces, the Gromov-Prokhorov distance is again the infimum over all epsilons, such that okay, now you isometrically embed both x and y in some common metric space Z. You push forward their measures, the measure of x and the measure of y, and now you use the Prokhorov distance to compare the measures. Okay, so that's completely analogous to the Gromov-Hausdorff distance, but it's now comparing measures. And there's a third thing that you could do, and it is to compare both the metric structure and the density structure. This is a stricter distance that is called the Gromov-Hausdorff-Prokhorov distance. And we do the same, we play exactly the same game. We consider all possible embeddings of x and y into a metric space Z. But now we compare the images of x and y using the Hausdorff distance and the push forward of their measures using the Prokhorov distance. And now I know that these are many definitions, but now I'm going to give you an example that should make many of these things clear. So the example comes from this observation. I claim that the Gromov-Prokhorov distance is in general strictly smaller than the Gromov-Hausdorff-Prokhorov distance. And the reason is the following. For example, here we have two metric probability spaces. Again, these are just finite metric spaces that I end up with a normalized counting measure. And we can see that their measure structure is very similar in the sense that I can embed both into a common metric space. For example, I can embed both into the second one. And once I do that, their measure structure is going to be very similar. The measures are essentially the same. But if once I embed this one in that one, I also compare the Hausdorff distance, then they're going to be very different because here I have points that are very far away from any point there, which are the points here. So this shows that this the Gromov-Hausdorff-Prokhorov distance is kind of distinguishing things that maybe we don't want to distinguish, and the Gromov-Prokhorov distance is kind of nicer because it's forgetting about these points that you may want to regard as outliers. But nevertheless, both distances are important, and we're going to use both. Okay, and then the last distance that I'm not going to say very much about is a distance to compare simplicial filtrations, and that is the homotop interleaving distance. And all we're going to need to know is that that distance exists. It's a nice distance that you can use to compare multi-parameter simplicial filtrations. And we don't really need to get into the definition for the purposes of this talk. Great. So here we have two distances, the Gromov-Prokhorov distance and the Gromov-Hausdorff-Prokhorov distance. And here we have the homotop interleaving distance. And we want to study the stability or continuity of maps of this form. And we're going to say that such a map is stable if it is Gromov-Hausdorff-Prokhorov continuous, or if you want it to be uniformly continuous or Lipschitz, that's also okay. And we're going to say that it is robust if it is Gromov-Prokhorov continuous. So being robust is stricter, it's stricter than being stable. And stable is just basically just checking that our construction is okay. Like if we give it two things that are very close in the Gromov-Hausdorff-Prokhorov distance, then we really want it to return things that are very close. Otherwise, it's not really what we want. Okay, and just a comment here. If you are used to the to the Wasserstein distance or to the Gromov-Wasserstein distance, you can basically think of the Wasserstein distance as being equivalent to the Prokhorov distance. this is essentially true. It's not Lipschitz equivalent, but in terms of convergence and in terms of uniform bounds, it is the same. Okay, so these are the two main properties we're going to be interested in, and let's see some of these filtrations. So let's start with function Rips, and for that we're going to need the definition to recall the definition of a subcomplex of a simplicial complex K spanned by a subset of its vertices. So whenever we have a simplicial complex K and we have some subset of its vertices, we can restrict the simplicial complex just to that subset of vertices, and that's what I'm going to call the subcomplex spanned by that set of vertices. So using this idea, we can just try to, we have Vietoris-Rips, which is a filtration. We can try to filter it in another direction using some density estimate in order to get rid of the noise points. So this is a very specific version of function Rips in which I'm just going to consider density estimates. You could do function Rips with any sort of function that you want, but for the purposes of this talk, I'm going to call function Rips to Vietoris-Rips filter by a density estimate. And what you get is a 2-parameter simplicial filtration. And the way you get that is you first take Vietoris-Rips. So this has 2 parameters, T and K. You take Vietoris-Rips, and now you consider all the points, all the vertices of X, of Vietoris-Rips of X, which are the same thing as the points in X, that have a density estimate that is larger than K. And in this way, you filter your Vietoris-Rips complex, and we're going to see a picture in a second. But this is the definition of function Rips. And again, we are just going to consider function Rips in the case F is a kernel density estimate, which is often defined like this. This is some kernel. And if you haven't seen this formula before, this is just basically taking some neighborhood S and seeing basically how many points X has in the neighborhood S, and counting how many points gives you an idea of whether X lives in a high density region or not in a high density region. So in particular, to build a kernel density estimate, you need to fix a bandwidth. But let's suppose we have fixed a bandwidth. That gives you a function, which is a kernel density estimate, and we can use that function to filter Vietoris-Rips. So let's see how this looks in an example. This is basically the circle that we had in the very first slide, and it is colored by a kernel density estimate that I have built using a radius that is relatively small, maybe a radius like this. I think I chose something like that. And because of that, you have points that are very light, of a very light color on the circle, and darker in the middle and here. Okay, so that looks like a pretty reasonable density estimate for this data set. And in fact, if you run function Rips with that kernel density estimate, you get something very reasonable. So let me tell you what this is. This direction is the Vietoris-Rips direction, and this direction is the density direction. So so here you have the original data set, and now if you run Vietoris-Rips, you get what you would expect. You get something that doesn't really look like a circle. Here I'm just drawing the one simplices of Vietoris-Rips to make the thing a bit nicer, but you can see that basically you don't capture the circle basically at all. Whereas when you filter by these density estimates, since these have very low density, at some point of the filtration by density, you get a nice circle. And now when you do Vietoris-Rips, you get a very nice circle. And even if you go lower, maybe here you start missing stuff, but Vietoris-Rips is still pretty good at eventually capturing the circle. So in the end, you get like a large portion of this filtration that really captures the circle that you should be capturing. Okay, but remember that we had to choose a bandwidth. And the point is that if you every time you make a choice, you can make a mistake, and that can easily happen. For example, say that I chose a radius for my density estimate that is maybe very large, so that this point here, I'm considering all these neighbors, so that the things that end up having the largest density estimate, are the things in the middle of the circle. In that case, if I do exactly the same thing, I'm never gonna find the circle. So this is a usual Vietoris-Rips that doesn't find the circle. And now if I start filtering by density, since these are the ones that have the highest density, the stuff from outside starts disappearing and the stuff from inside is always there. So regardless of what I do with this filtration, once I fix that wrong bandwidth, that's it. This filtration is never going to see the circle. So it doesn't matter in what part of the filtration I look for it, I won't find it because I made a poor choice of kernel bandwidth. And that's the problem with fixing parameters. So so a way to fix that is to try to not fix the kernel bandwidth. And that's what basically degree-Rips does. So degree-Rips does it in a specific case, and then there's kernel-Rips that does it in a slightly more general way. So the way degree-Rips does it is it takes Vietoris-Rips again, but now filters it by the degree of the vertices in the one skeleton. So this was introduced by Lesnick and Wright, and the definition again is take Vietoris-Rips. Again, this has two parameters, T and K. This is density, and this is scale. And now you take Vietoris-Rips at distance scale T, and you just take the subcomplex that is spanned by the vertices of degree at least K times the number of points in X. And if you want to forget about this, it's okay, it's just a normalization. So you take just the vertices of degree at least K. And the nice thing about this is that the vertices of degree at least K are basically a kernel density estimate. I mean, the degree of a vertex is basically a kernel density estimate. And since you're taking the vertices of degree K in Vietoris-Rips of T, you're fixing the bandwidth to be T too. So what this is saying is that we are taking Vietoris-Rips and then we are filtering it by a kernel density estimate, but the bandwidth is the same thing as, is exactly the same as the density scale that, as the distance scale that we're using for Vietoris-Rips. So in particular, we are not fixing it, it's varying with T, and it's not gonna have the problem that function Rips was having before. And in fact, if you draw a plot of this construction, in this example, you're gonna get something similar to this one. So it's gonna work very well. Okay, so then given that basically the degree of a vertex is essentially a kernel density estimate, it's not too hard to generalize this and come up with kernel Rips, which is basically just a generalization of degree Rips and our version of function Rips, in which we just take Vietoris-Rips and we filter by some kernel density estimate, but we don't fix the bandwidth and we just put it as a third parameter. So kernel Rips has three parameters. One is the kernel bandwidth, one is the distance scale for Vietoris-Rips, and the other one is the density threshold. And the nice thing is that this has pretty decent stability properties. So it is Gromov-Hausdorff stable. In fact, it is uniformly continuous. And if you use some like very specific kernels, like for example, if your kernel is a square kernel, then it is 2 Lipschitz. So it's actually Lipschitz. And this Gromov-Hausdorff procore of stability basically gives you stability results for the degree Rips and for function Rips when you use, in that case, a continuous kernel to construct function Rips. So
Luis,
okay.
can I ask you a question?
Yeah.
So the kernel Rips, it's sort of monotonic or weakly monotonic in T and in K. Is it also monotonic in S?
Yes. So that's a good question. I was trying to. So yes, the thing is, look at the kernel density estimate that I'm writing here. So
I see.
I don't, since my point cloud doesn't live in any specific Euclidean space, I don't have any way of normalizing this. Like usually you would have something of the order of, what is it, n to the power of d, something like that. So you have the dimension of the Euclidean space. Sorry, not n, sorry, this. But in this case, since this is not living in any Euclidean space, I don't have access to any specific D. So I'm just forgetting about this term. And that this makes it monotonic in S. As I make S larger, this gets larger.
Gotcha.
And I mean, that seems weird in the beginning, but it is really the only way to make, to not fix S. If you don't want to fix S, then you want to let it vary. But then you, in order for it to be a filtration, it better be monotonic. And it's
right.
funny, you just forget about this term. And if you want to reintroduce it later, you can do that. If you somehow choose a one-dimensional slice and you want to reintroduce it to get a true density estimate, you can do that. So it's just kind of a trick.
Makes sense. Thanks so much.
Yeah, thank you for the question. And in some sense, it is also natural because the degree is also like an unnormalized density estimate, because you're not reintroducing that 1 over t that, or 1 over t to the power of t that should be somewhere. Okay, thank you for the question. So, right, we have the stability result. So this is just Gromov-Hausdorff Prokhorov stability. It's kind of strict, but it is true. But then, yeah, the issue is that this doesn't guarantee robustness. And in fact, you can show that this is not robust in the nice sense that we want it to be robust. So this is not Gromov-Prokhorov continuous, and not obviously not Lipschitz or uniformly continuous. So how can we fix this? I think this is due to Sheehy. He has this version of Vietoris-Rips in which he, instead of filtering Vietoris-Rips, he filters a subdivision of Vietoris-Rips. So in order to explain that, let me first recall what the subdivision of a simplicial complex is. Suppose that I have a simplicial complex. The subdivision is just take the complex, first put a simplex, put a vertex in the barycenter of each simplex. So here I have a 1 simplex, I put a vertex in the middle, I have a 2 simplex here, put a vertex in the middle. I do that with all simplices, and then I connect them and basically partition my simplices, do the barycentric subdivision. And now the observation is that the vertices of the barycentric subdivision are not all made equal in a sense, because this vertex, for example, comes from an original vertex in the simplicial complex, whereas this vertex is the barycenter of a 1 simplex. And this vertex, for example, is the barycenter of a 2 simplex. So I have some notion of grading for these vertices. And more precisely, I can just assign what I'm calling a dimension to each vertex of the barycentric subdivision. And now I can just filter by this notion of dimension. So I can remove all the ones that are of degree 0 and lower, and then I can remove all the ones that are of degree, or rather dimension 1 and lower. And then in this case, if I keep going down, I just get the empty simplicial complex. But the point is that the subdivision of a simplicial complex has a filtration that has to do with the original dimension of the simplices. And then I can apply this to any simplicial complex. So I can take Vietoris-Rips, take its subdivision, and then filter it by the original dimension of the simplices. And this again is some normalization constant that you can forget about. The only issue with this construction is that it's pretty hard to visualize because the subdivision of a simplicial complex has exponentially many vertices. So if you started with something with n vertices, it could have potentially exponentially many simplices, and then the subdivision is going to have exponentially many vertices. So it's gonna be huge in general, but you can still define it, and you can still study it theoretically, and maybe you can still compute the homology using some clever algorithm. So we'll see how much of that was done. So first of all, the theory, Bloomberg and Lesnick proved that subdivision-Rips is Gromov-Prokhorov stable. So it is robust. And that is, I think that is super interesting because, I mean, you're just looking at Vietoris-Rips, you're not taking any density estimate, any kernel density estimate whatsoever. You're just taking the subdivision, and somehow the subdivision and these degrees in the subdivision, or these dimensions in the subdivision, are capturing a lot of the density structure. So I think that's very interesting. Then a few more things about the subdivision filtrations. So
Can I
the
ask?
first thing that,
Sorry.
is there a question?
Yeah. So can I about the previous slide?
Yes.
In what sense does the reference probability measure appear in the subdivision? That's something I didn't understand.
Right. So that's an excellent question. So here, the subdivision-Rips filtration is really only defined when you have a metric space, a metric probability space that comes from a finite metric space with a normalized counting measure.
I see.
And then the measure is appearing here, basically, is this normalization. You can extend it to arbitrary compact metric probability spaces, basically by taking arbitrarily good samples of increasing number of points. Since a sample converges in the Gromov-Prokhorov distance to the space you're sampling, and since this is Gromov-Prokhorov stable, you actually can define the subdivision-Rips of an arbitrary compact metric probability space by taking a limit, but I don't know if that's studied anywhere, and I don't know how easy it is to work with that, but you can define it for an arbitrary one by taking samples.
Thank you.
Thanks for the question. Okay, so this is robust, and okay, so that's great for applications, but of course I said that this has a lot of simplices, so you have to come up with some way of computing it, and also you might want to know what homotopy type this is capturing. Like, okay, this is robust, fine, but what is this simple shot filtration? What is it capturing in the limit, for example? And there are relatively nice answers for both problems. So in order to give the answers, I need to introduce the subdivision check filtration, which is just the subdivision of the check filtration. We do the same thing. You do the same thing as with the Vietoris-Rips filtration. Imagine you have a subset. In this case, you can take it to be finite of an underlying metric space. You take the check filtration, and then you take the subdivision of it. You filter by the dimension. So in terms of what the subdivision-Rips filtration is computing, there's an answer that goes as follows. So again, in the case you have a subspace, a finite subspace of some metric space, you can define the multi-cover filtration to be, so this is going to be a filtration of E, and it's going to have the, at scales T and K, it's going to have all the points in E that are at most T far away from at least K times N distinct points in X. And if you want, this is again a normalizing constant. So this is the important part, K. So instead of doing check, where you put a point whenever it's close to one of the data points, you do check, but you put a point whenever it's close to at least K of them. And that gives you another direction. And it makes it more robust because you don't appear in the filtration as soon as you're close to one, but you have to be close to many. And this was introduced by Shihi, as far as I understand. And in fact, he proves basically a nerve theorem. It's called the multi-cover nerve theorem, which tells you that if you have a good metric space, this is a metric space in which balls are contractible and any intersection of balls is contractible too. If you have a good metric space, such as the Euclidean space, then subdivision check of X has the same homotopy type as the multi-cover filtration of X. And here I'm missing an E. But so this is analogous to the if you take K equals 0, K equals 1, or rather Kn equals 1, then this is the usual nerve theorem for the check filtration. Okay, and then to say something about Vietoris subdivision-Rips, you can note as done in work by Memoli, where is it, Okutan? I don't remember the third author name. That Vietoris-Rips is the same thing as check in an injective hull. So if you take an injective hull, Vietoris-Rips is the same thing as check, and then that that holds for the subdivisions, and then you get the same thing as the multi-cover filtration. So in the end, subdivision-Rips is basically computing the homotopy type of the multi-cover filtration in any injective hole. Okay, so that is what subdivision-Rips is computing. This is a possible answer. And then about the computation, how can you do stuff in practice? There's work by Edersbrunner and Ozang, and Corbet, Kerber, Lesnick, and Ozang, in which when you combine the two works, you can compute the homology, or rather approximate the homology arbitrarily well of this two-parameter filtration in polynomial time. And now the exponent depends on the dimension of the point cloud, or where it is embedded, and the base is just a number of points. So in practice, for low dimensions, you can compute that for the subdivision checkpoint. Okay, so with all of that said, we can fill in this table. So we started with function-Rips. We know that it is basically stable. The problem is that you have to choose a parameter, and it is not robust. Now, function-Rips, as other ones, has this super interesting or super useful property, rather, which is that the zero simplices of the filtration are the data points. And that, I think, that is very crucial for interpretability. For example, if you're doing clustering and you have a connected component of your filtration, then that's exactly a cluster in your data. So I think that having vertices, having the filtration be a filtration on the data is usually a very useful property. And function-Rips definitely has that property. And it is easy to calculate the homology in polynomial time. I mean, assuming you know how to compute minimal presentations and all that fast, which is non-trivial, but you can do it. Then degree-Rips and kernel-Rips improve on function-Rips, basically by making them parameterless. And we've seen that that is actually useful in practice. Sometimes choosing the bandwidth, the kernel bandwidth is not easy, especially if you don't know anything about your data. And these still have the property that vertices are data points. And in particular, in work with Alexander Rowley, we use kernel-Rips to do density-based clustering, and I think it works really well. Now, subdivision-Rips has this property that none of the other ones has, which is being robust, but it comes at basically two costs. One is that the vertices are no longer data points. The vertices are subsets of data points because they are simplices in the original Vietoris-Rips, and these are not even disjoint. So in order, for example, to do clustering, it's not clear how you would translate a connected component of subdivision-Rips into a subset of your original data. And it is huge. So in order to compute the homology, you have to do pretty clever stuff. So this is clever stuff done for the subdivision check. Rather, this is clever stuff done for the subdivision check. For the subdivision-Rips, as far as I know, there aren't algorithms yet to compute the homology fast. So my questions are, is there a robust filtration where the vertices are the data points? I think that would be super useful. Then something that is super interesting is that, and this is also observed by Lesnick and Bloomberg, and they give an example in their paper, that degree-Rips and also kernel-Rips tend to work in practice much better than what we can prove in theory. So the robustness results that we have for degree-Rips are pretty weak, but in practice, they are very robust or pretty robust. So an interesting avenue is to actually try to prove better and like more precise robustness results for these two filtrations. And then finally, there's the question of, can we compute the homology of subdivision-Rips in polynomial time, basically. And that is all I wanted to tell you. Thank you. Thanks a lot for listening. And yeah, I'll be happy to discuss more.
Thanks a lot, Luis, for the talk. So I suggest we unmute ourselves and thank Luis. Are there any questions for Luis? maybe I'll start with one.
I can
questions.
ask one, Facundo.
Yeah, please go ahead.
It's more of a comment. So you have stability and robustness. You know, if you start with the two terms, you would think that if there is a stability result, it should be robust also, but it's not. So is there a way to combine the two, or can you give one property that captures both somehow? And maybe some of these filtrations have already that, or maybe you have to put more to say that, or do we have to really consider those two separate?
So, I mean, robustness. So we do have the Gromov-Prokhorov distance. The Gromov-Prokhorov distance is always smaller than the Gromov-Hausdorff-Prokhorov distance. That means that if you are stable with respect to this distance, then you're also stable with respect to this one. And being stable with respect to this one is being
wait a minute.
And being stable with respect to this one is what I call stable. So what this means is that being robust implies being stable in the sense that I.
Not the other way.
Now the problem, I mean, yes, that's great, but the problem is that coming up with robust filtrations is hard. And so that is why I am considering this, because coming up with stable filtrations, that is much easier, and we have a good amount of those. So basically, yeah, the problem, like that is the problem, going from this to that, and that's why I have to introduce this, because this is what we know, and here there is basically only one or two filtrations that we know of, and all of them are very big filtrations. They are not filtrations on the data points, so there are many things to still be fixed there.
I have one quick question. So is there any special results so if you look at this taxonomy here, does it become better for multi-parameter clustering of metric measure spaces? I wonder if there are many methods that may satisfy more of the boxes.
When you only care about connected components?
Yeah.
So I don't think so. I mean, or at least all the results that I'm aware of, maybe they're only stated for for connected components, but you can easily extend them to the rest of the homology. But I mean, that could be like a good thing to try, because maybe yes, maybe I'm trying to do too much, or we are trying to do too much, and we should focus only on one homology, maybe zero. And so, okay, maybe an interesting thing is that for some filtrations or for some constructions, you can prove robustness results for homology that is not H0. And the reason is that there are some constructions, like some metric learning algorithms that take your data set, and what they do is they push the outliers further and further away, and they keep this. So then in H0, this is not robust, because each of these outliers is going to give you a new connected component. But in terms of H1, this is robust, in the sense that the only like H1s that you're going to see are the ones that do not come from outliers, because you push the outliers very far away. That I don't know, what you said reminded me of that.
And I have a question about your description of a multi-cover filtration. I forget the slide number, but so somehow when you were showing this formula for MXETK, reminded me of something called the distance to measure that was suggested by Chazal and Marigot and some other colleagues. And I was wondering if one could see the multi-cover filtration as something like doing check on top of a subset of the original space where you filter by the kth distance to measure. I don't know if you're familiar with that.
Yes. I think this can be rephrased using the distance to measure.
I see.
Right now, I don't want to write it down because I will make a mistake, but but yes, I believe that's true, and that is, they mentioned this in this paper,
Okay.
where they prove this this robustness result for subdivision Rips and subdivision check.
Thank you.
Luis, I want to ask a question about the subdivision Rips, if you don't mind going to that slide. Right. So, okay. So, I mean, I think your talk is mostly in the setting of finite point sets, right? But you talked about how you could do this in the setting of infinite point sets. So, if I want to think of subdivision Rips of a manifold, and we'll just take the circle. I think maybe you can make sense of this. So, you know, I take the standard Rips complex of the circle, but now I'd look at the barycentric subdivision, right? And in the Rips filtration parameter, which is the same as always, increasing the diameter. But then in the sort of barycentric subdivision dimension, you're sort of throwing out the simplices of their barycentric subdivision that correspond to few vertices. Is that right? So you can sort of define the subdivision Rips of, say, a circle, and it's a 2-parameter filtration. Is that correct?
So I think in order to make it work, because of this normalization, you cannot strictly take subdivision Rips of an infinite set.
But just get rid of the normalization, and the other parameter is just that K.
So I just forget about this. Is that what you're saying?
Yeah. So I have this 2-parameter filtration. If like K is 0, then I just have the barycentric subdivision of the usual Rips. Right. And then as I increase K, I'm just looking at higher and sort of.
Okay.
Does that make sense?
Yes, I mean, you can do that. Yes.
Okay.
I think the way to you can use this theorem to define. So if you have say that you have a metric probability space Y, and I want to define subdivision Rips of it, then I think one way to do it is to take a colimit where X, or if you want Ym, is a finite sample of Y. And then I do subdivision Rips of Ym. And now I use the normalized counting measure here.
I see.
And since Ym is converging to Y in the Gromov-Hausdorff distance, and since subdivision Rips is continuous, and you also need to know that the space of multi-parameter filtrations is complete, but that's true, then you can take this colimit.
So,
and do you know if that gives something different than what I said?
I suspect it will give you something different because you're not using the normalization. So in particular, all your jumps are going to be at integers, and here the jumps are all between 0 and 1.
Okay. Right, but like my thing had like a discrete parameter, whereas yours really has a continuous parameter. Okay.
Right.
Interesting. Yeah, I'd like to learn more about this. Thanks.
I kind of want to piggyback on the previous question. And what about the following possible generalization? So dimension is counting essentially the number of points, right, that you're contemplating in the subset. And suppose you divide by cardinality of X, then that is consistent with saying that the normalized counting measure, the uniform, the finite set of points is lower bounded by K. But now, right, when applied to the subset, to the simplex, you're asking that the measure of the simplex is at least K, right? But if you have any other measure, say mu, you can still say, I will consider this simplex to be my filtration if its measure mu is lower bounded by some number kappa, and that seems to simply generalize the definition.
Yes. So the problem that I see with that definition is that if your space is continuous, like if you want to apply it to a circle with like the Hausdorff measure, like the uniform probability measure where every little piece measures the same, then every point has zero measure. So if you take any simplex, simplices have finitely many points, they're all going to have zero measure.
Right.
So that's why I'm doing this contrived thing.
Kind of asking for an extra parameter, right? To take some sort of thickening of simplices or something like that. Yeah, I see. Okay, thanks. That clarifies. Yeah. I think as I was starting to speak, I heard someone else's voice. Sorry for interrupting, but please go ahead with your question.
Yeah, sure. Sorry, I'm on a train, so I hope you can hear me. I was just going to ask, Henry. He mentioned this this possible construction about subdivision-Rips of something like a circle, and I was just wondering if he has any like intuition about what that would look like. What he was, because it's not. I was just trying to think what would happen if you considered that for k, for like positive k. And I'm not sure what my intuition is for what you would get. I was just wondering if anyone has some intuition.
I'll say I don't, but I mean, and that's exactly the question I had in mind, Alexander. Like if you define something like this for the circle, then what are the homotopy types? I think is why I'm interested. Yeah.
Right. I don't know. The circle is so symmetric that I feel like if you do some sort of density filtering of it, either you get the circle or you just don't get anything.
Yeah, I was wondering if it would just always be the circle, but with these, I don't trust my intuition with this. So.
Me neither. I think these subdivisions filtrations are super interesting, but it's hard. At least for me, it's hard to think about them. Yeah, I don't know. I think that the main point is to use them when there is some noise. So maybe like no, I don't know. I think that's a good question because since it is robust, the noise shouldn't matter. So you really want to know what happens when you apply it to the circle. Right. That would be an interesting computation.
Are there any more questions or comments? All right. So I'll stop recording, but if people want to hang out, I think that should be fine. Thanks again, Luis, for the wonderful talk.
Thank you very much.